So before we dive into the content about algebraic extensions today, I want to just draw a picture, a Venn diagram, you might say. This box represents, say, all complex numbers. That's the complex number field. I mean, usually we work from smaller number systems to bigger. I guess I'm doing the reverse here, going from bigger to smaller. That's the complex number field. Every point in there is of the form a plus b times I, where I squared equals -1 is the imaginary unit. It does have the real number system as a subfield. You might say a relatively small subfield, but I'll draw it bigger than I arguably should. There's the real number system. Of course, the more typical way to visualize this is that C would be the complex plane. You would draw axes, think of the plane of the paper as being the complex plane, points in that plane as being complex numbers. When you do, you label the horizontal axis with the word real and the vertical axis with the word imaginary. But it is there. I did draw it. It's on the paper. It's just a label. It's just labels. Okay. Don't think too philosophically about this. It's just labels. It's just ways of conceptualizing things. And an arbitrary complex number, a plus bi, is a point in this plane. And its coordinates, its rectangular coordinates, would be a comma b. This number right there would be a. This number right here would be b. Where is the I in the picture? Well, it's, I is 0 plus 1 times I. In the plane, its coordinates would be 0, 1. It would be right there. That would be the complex number I. Just like the real number 1 would be right here, say. And 1, yes, 1 could be thought of as a complex number as 1 plus 0i. Any real number, in fact, x could be thought of as a complex number, x plus 0i, and would be in this picture on the real axis. So here, the real number system is just the real axis inside the complex plane, a one-dimensional line inside a two-dimensional plane. Okay, these are both fields. They are both vector spaces over, for example, the real numbers. The real numbers as a vector space over itself would be one-dimensional. A basis would be, for example, the number 1. Or in fact, any non-zero real number would be a basis with one element for the real numbers over itself. The complex numbers as a vector space over the real numbers, where the scalars are real numbers, and the vectors are complex numbers, you can multiply a complex number by a real scalar and get a complex number. Would be a two-dimensional vector space over the real numbers. Basis would be 1 and I, for example. And that kind of makes geometric sense. Anyway, coming back to this picture, the real numbers are a subfield of the complex numbers. The complex numbers are a field extension of the reals. The rational numbers are, say, right here, Q. That's a subfield of the real numbers and therefore also a subfield of the complex numbers. The real numbers form a field extension of the rationals. The complex numbers form a field extension of the rationals. It's a subfield of the reals. So in this picture, it's on the real axis. They're all the points that correspond to rational numbers, which there are infinitely many of, right? One thing you're going to learn in real analysis is the number of real numbers is a bigger size of infinity than the number of rational numbers. There are different sizes of infinity. Have I mentioned that before? It's called cardinality. You can make an official definition of size of infinity, so to speak, and you can prove the real numbers are a bigger size of infinity called uncountable than the rational numbers. The rational numbers are countable, countably infinite. You'll learn about what that means in real analysis. In a sense, even though there are infinitely many rational numbers, and even though between any two rational numbers, no matter how close they are, there's another rational number, in fact, infinitely many, there's still somehow more real numbers. You can kind of make a little bit of intuitive sense out of this if you think about both rationals and irrationals in terms of decimals. We know rational numbers either have finite decimals that truncate or infinite repeating decimals, and irrationals are all of the others. And if you sort of think intuitively, non-repeating decimals probably are, yeah, it sort of makes some intuitive sense that there are more of them than there are repeating decimals, because it's just the random. I mean, you could talk about random digits or something like that. So that's a slight intuition that hints at the fact that the irrationals are uncountable and the rationals are countable. But yes, the irrational numbers are all those real numbers that are not rational. And that does include, for example, square root of 2. Pretend that's right there. Cube root of 2, pretend that's right there. Fourth root of 2. Maybe that's over here, right? Okay, drawing these in certain locations is kind of silly, but just for the sake of fun, draw them in different spots. You've also got fifth root of 2, sixth root of 2, seventh root of 2, blah, 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 blah. You also have square root of 3, cube root of 3. Of course, you also have things like pi and e in here somewhere. Pi, e, pi squared, e squared, infinitely many of them. Yeah, and they're all irrational. Some of them are what's called algebraic, and some of them are what's called transcendental, and that's one of the main themes for today. Algebraic versus transcendental. Of course, you also have the integers in here. Let's say that's z. Though the integers don't form a field, they form just a plain old ring, technically a special kind of ring called an integral domain. But they don't form a field, so therefore they're not a subfield of Q or R or C. And technically that also means Q, R, and C are not field extensions of Z because Z is not a field. But it is a number system that's got all your ordinary integers, like 4, for example. And all those are rational numbers. 4 is 4 over 1. It's also 8 over 2. Of course, you only need one of those representations. And those are real numbers, and they're also complex numbers if you do this kind of identification. Actually, the picture gets even bigger. Complex numbers is not the biggest number system. There's also something called the quaternions. There's also something called the octinions. Are they always powers of 2, 4? Two-dimensional. Quaternions are what, 4-dimensional? Yeah. Octinions are what, 8-dimensional? Yeah. Wait, what would the next one be? 16-tinions or something? Okay, octinions sounds like far enough for me. Anyway, though the quaternions and the octinions, though, are actually not fields. They actually don't satisfy commutative property. They're not commutative. They are rings, and they're almost fields in the sense that they do have multiplicative inverses, but somehow they're not commutative under multiplication. It's called the division algorithm. Division algebra is the official name for it, but they're actually not quite fields. Anyway, our main topic for today, though, is the distinction between algebraic numbers and transcendental numbers. Every rational number is an algebraic number. Some irrational numbers are algebraic and some are not. Roots like square root of 2, cube root of 2, fourth root of 2, etc., square root of 3, cube root of 3, etc., blah, blah, blah. Roots like that are algebraic. But it turns out numbers like pi and e are not algebraic. They're transcendental. And even though we're far more used to algebraic numbers, the transcendental numbers are weird. There are actually countably many algebraic numbers and uncountably many transcendental numbers. Whoa. I'll let you ask Dr. Auk about that in real analysis. All right, so let's get into wrestling with these ideas in detail now. What is the definition of an algebraic number? Well, it's not, okay, this definition is a generalization of that definition. So we're talking about any fields and field extensions here, not just rationals and field extensions of the rationals. Let E be an extension field of F, and let A be an element of E. So I guess I will draw another picture. Here's F, that's your base field, and I guess I'm switching the role of colors here. Here is E, that's your extension field. It includes F. Let A be an element of E. Does that mean A is not an F? Not necessarily. A could be an F, but it's more interesting when A is not an F. So typically you imagine A to be outside of F, though that's not required in the definition here. We call A algebraic over F if A is the zero or root of some non-zero polynomial in this polynomial ring. Polynomial ring with coefficients in the smaller field F. When F is Q, the rationals, that's when we be a bit more specialized and we're say A is an algebraic number. When you just say algebraic number without qualifiers, like what the base field is, you are talking about it being algebraic over the rationals. The base field would be the rationals in that case. If A is not algebraic over F, it's called transcendental over F. Notice the over F in both cases. So a number could be algebraic over one base field, but not algebraic over another one. It could be transcendental over another one. But again, if the base field is the rationals, then we sometimes use the words algebraic and transcendental without saying over. An extension E of F is called an algebraic extension if every element of E is algebraic over F. If E is not an algebraic extension, if there's at least one transcendental element in it, it's called a transcendental extension. If the extension of F is of the form F of A, and remember that's not function notation, that's the smallest subfield of E containing all of F and the element A. If the extension is of that form, it's called a simple extension. Those are the simplest kinds of examples to think about. Okay. I'm going to briefly talk about transcendental extensions right now, but not say much about them. For the most part, we just study algebraic. They're much easier to understand. Okay. Well, okay, there will be another theorem we'll look at where we'll talk a little bit more about transcendental extensions. But what I'm going to say right now is, yes, pi is a transcendental number, meaning it's transcendental over the rationals. Q adjoining pi is a transcendental extension. It's got pi in it. By the way, proving pi is transcendental, proving that it's not the zero of some non-zero polynomial with coefficients in the rationals is very, very difficult. People suspected it. Back in the 1700s, people like, it doesn't seem like pi solves any polynomial equation with rational coefficients. But proving it had to wait till the late 1800s, and many people tried over many years. It's a hard proof to prove pi is transcendental, that it solves no polynomial equation with rational coefficients. But anyway, now we know it does. It doesn't satisfy, so it's transcendental. So this is a transcendental extension, and the author makes a comment here, and this is actually going to be relevant to the theorem where this will come up again, that while Q adjoining square root of 2 has elements of this form, as we've seen, Q adjoining pi has elements of this form. Effectively, rational functions where the coefficients are rationals, where pi is plugged in, are the elements of that field. Say it again. That expression is effectively a rational function, a ratio of two polynomials, where the a's and b's are all rational numbers, And the plot, you replace the x with pi. Plug in pi into the rational function. The set of all such numbers that you can create in that way turns out to be the best way to describe q adjoint pi. So we'd have to talk about rational functions. We have to go beyond polynomials if we're going to understand transcendental extensions. Yeah, we want to focus on algebraic extensions, especially simple ones like this, right? Isn't this starting to feel, that this example here starting to feel simple relative to the rest of everything you're reading? Help. Okay, so let's go back to our example from Wednesday. Talk about the same example again, and then we'll extend the example. And I did figure out what I was wrong when I was thinking about that one other way to think of it with a ring homomorphism. I figured out what I was thinking, how I was thinking about it wrong, and it's actually related to the next theorem. So we're thinking about this example, q adjoin root 2. I'll remind you, this is the smallest subfield of, for example, the reals. But you could mention other field extensions like the complex numbers as well. Containing all the rationals and also containing square root of 2. But once more for emphasis, it's more than just the rationals and one number square root of 2. There's plenty more numbers. Like 1 over square root of 2. Square root of 2 cubed, which is 2 times square root of 2. Things like that are in here. And in fact, it takes proof. You can prove, as was just mentioned, that it's the set of all numbers of the form a plus b times root 2 as a and b varies over the rationals. Won't write it down, but I'll emphasize again, this means, turns out that it's a two-dimensional vector space over the rationals because two things. This expression is a linear combination of the two numbers 1 and square root of 2. So it's a span of those two numbers. Just the set of two numbers 1 and square root of 2 is a spanning set. Rational scalars, not real. These are rationals. And it turns out the set 1 comma square root of 2 is linearly independent over the rationals. If this equals 0, the only way that can happen is if a and b are both 0. And the reason is ultimately because square root of 2 is not rational. So, by the theory of vector spaces, the set 1 comma square root of 2 is a basis for this as a vector space over the rationals. It's a two-dimensional vector space, and that is important in chapter 20. This is an algebraic extension. In fact, you could say it's the splitting field, or a splitting field, for the polynomial f of x equals x squared minus 2 over the rationals. Why? What does this mean? A split, to say f of x splits in some field extension means you can completely factor it in that field extension. We know x squared minus 2 can be factored because its roots are plus or minus square root of 2 as x minus root 2 times x plus root 2. Certainly, this means f of x splits in any field extension of the rationals that does contain square root of 2, of which this is one of them. And in fact, this is the smallest such field. Therefore, it is a splitting field. Well, okay. And it is, since again, square root of 2 is a root of this polynomial, it is an algebraic extension. Technically speaking, you'd have to prove that any number of this form is the root of some polynomial with rational coefficients, but that's not too hard. Okay. So this is an algebraic extension. let's look at the next theorem. And in looking at it, the next theorem and its proof, we'll come back to the other way to think about this. Another splitting field that we form by doing a factoring, where we're modding by an ideal that's a principal ideal, that's maximal principal ideal, generated by an irreducible polynomial. This is irreducible over Q, by the way, again, for emphasis. And in fact, to prove it, you can use Eisenstein's criterion with P equal to 2. Let's look next at this theorem right here. Let E be an extension field of the field F. So again, F is the smaller field, E is the bigger field. A is an element of E. A could be an element of F, but it's more interesting when it's an element of E that's not an F. If A is transcendental over F, then the field extension, F of A, being a transcendental extension, turns out to be isomorphic to that. What's that? That is the field of quotients of F of X. I have mentioned this before. So F square bracket X represents the ring of polynomials with coefficients in F. F parentheses X represents what's called the field of quotients. It's essentially the set of all rational functions with variable X, where these polynomials are the numerator and denominator of the rational functions, and they are in the polynomial ring F square bracket X. So the coefficients are from F. And you're not dividing by 0. This turns out to be a field. You can add rational functions, you can subtract them, you can multiply them, you can divide them, you can find multiplicative inverses, at least if F of X is non-zero. Turns out to be a field. It's a field of rational functions, and a transcendental extension like this is isomorphic to that field of rational functions. And that's why on the previous page, this extension is the set of all numbers like this. You're effectively plugging pi into the rational function in place of X. Okay, so again, it's more complicated. That's fine. If A is algebraic, what we're more interested in over F, then, yeah, this is related to the example from last time. The field extension F of A, or for our example, Q of square root of 2, is isomorphic to a certain factoring. A factoring where you're modding the polynomial ring by this ideal, which is, it's a principal ideal. It's also going to be a maximal ideal because P of X is going to be, it's not said right until the end here, it's going to be irreducible over F. And in fact, you also pick P of X to be a minimum degree polynomial that has A as a root. Okay, and the proof is similar to what I was thinking about in class on Wednesday, but made some mistakes in thinking about it. Let's think about this proof in the context of our example. So they say, consider the ring homomorphism Fx to Fa. So for our example, that ring homomorphism would be from Qx to Q adjoin root 2. Again, Q is a field, but Q square bracket X is not a field. It's the ring of polynomials. It is an integral domain because Q is a field. It's also a principal ideal domain because Q is a field. These are theorems that were in earlier chapters that I'm alluding to here, but it's not a field. But it turns out this mapping where we're mapping F of X to F of A. So in our example, phi is mapping F of X to F of square root of 2. And that was where I made my mistake in class the other day. It was I put F of 0, I think, there. And I also put the wrong codomain. I want to think about the codomain of this mapping as being this thing, which is a field. That's not a field, but this is a field. F of square root of 2, F of X has rational coefficients, but I'm plugging square root of 2 into it. That's okay. You know how to do that. You can take a polynomial with integer or rational coefficients and plug a number like square root of 2 in place of X. You could plug a number like pi in place of X. But the result will be in this field. for as an example, if f of x is, take something simple like x cubed plus x, and you plug square root of 2 in there, you're going to get 2 square root of 2 plus square root of 2, which is 3 square root of 2, which is an element of this. Just an example here. Okay, it turns out in the general case, if A is transcendental, the kernel of the ring homomorphism, and you would want to prove this a ring homomorphism, is trivial. And through some other stuff, you can say that the this isomorphism holds. I'm not going to explain this about extending the isomorphism. What I'm more interested in is the second paragraph. If A is algebraic over F, then the kernel is not trivial. What is the kernel of this mapping? For our example, what's the kernel of phi? Well, it would be the set of all f of x in Qx such that this is 0. Certainly that includes f of x equals x squared minus 2, right? Because x squared minus 2 has square root of 2 as a root. And in fact, that's got to be with among polynomials with rational coefficients, that's got to be a polynomial that has square root of 2 as a root that's got minimum degree. Minimum degree. And it's irreducible over Q. Evidently, it's a generator for the principal ideal that we got to mod by. The kernel is going to be the principal ideal generated by x squared minus 2. That takes proof, but it's not hard, actually. You could probably use the factor theorem, maybe. Chapter 16. Prove that. And x squared minus 2 is irreducible over Q. This is a maximal ideal in there. Therefore, the first isomorphism theorem implies that if I make the factor ring, Q of x mod this maximal principal ideal is going to be isomorphic to the image of this ring homomorphism here. But what's the image? Is this onto? Yeah, it is onto. Give me an arbitrary element a plus b root 2 in here. What's a polynomial that gets mapped to it under phi? F of x equals a plus bx would. You can use a linear polynomial. Would get mapped to a plus b root 2. It's definitely an onto ring homomorphism. Therefore, I can say this is isomorphic to this. And yes, I can think of this, like I talked about on Wednesday, as being also a splitting field for x squared minus 2 over the rationals. Though it's a different kind of field than this is. But they are isomorphic. And as I emphasized on Wednesday, even though the elements of this are cosets of the form, well, maybe to be consistent with this notation, a plus bx plus the ideal, it's natural to think of all the cosets where b is 0 as being rational numbers, even though they're technically not. Effectively, you're identifying all cosets of this form, a, where b is 0, a plus the ideal as being rational numbers. Even though they're not rational numbers, they're cosets. But that's the kind of thing that algebraics do, is they don't distinguish between isomorphic things. Before we go on, maybe we should think about another example. How about Q adjoin cube root of 2. We thought about Q adjoining square root of 2. We also did think about adjoining square root of 3 last time, and doing both, in fact. Now let's do a cube root of 2. So again, when you look at this, the first thing that should come into your mind is, oh, that's the smallest subfield of the real numbers, containing all the rational numbers and also containing cube root of 2. But yes, as Dr. Kinney always warns me, it's much more than that. There's infinitely many other numbers in it. What other numbers? What is the form of this? Of elements of this? Say as a vector space over the rationals. Let's go back to a theorem in a previous chapter. This is a key theorem. And effectively, the other theorem in chapter 20 is very similar to this in some ways. Effectively saying the same kind of thing there. Though it's not mentioning algebraic numbers yet. Algebraic elements. Let F be a field, let P of X be in the polynomial ring with coefficients in F, be irreducible over F. If A is a 0, P of X in some extension, E of F, meaning, because of chapter 20, A is algebraic over F, then this F adjoin A is isomorphic to this factor ring, just like we saw in the other theorem. Furthermore, if the degree of P of X is n, then every member of F of A can be uniquely expressed in this form as a linear combination of powers of A, including A to the 0 power, which is 1. A to the 0 power, not shown, A squared, A cubed, through A to the n minus 1 power. The C's are all from the base field. If the base field is the rationals, the C is all rational numbers. So for our example, yes, the base field F is the rationals. And the A is cube root of 2. Cube root of 2 is a root of P of X equals X cubed minus 2, which is irreducible over Q by Eisenstein with P equal to 2. It's not irreducible over the reals. It's reducible over the reals. In fact, you can factor it. It is if you think of it as X cubed minus 2 to the 1/3 cubed, yes, 2 to the 1/3 is the same as the cube root of 2. It's the difference of two cubes, and so you can factor it with the formula for how to factor the difference of any two cubes. Can I get it right? I think it would be this. That's how you can factor it over the reals, not the rationals, right? Because cube root of 2 is not a rational number, though we've never proved that. That would be a factorization. Not a complete factorization, but a partial factorization over the reals. Not over Q. You might wonder, can I factor this one further over the reals? The answer is no. This one turns out to be irreducible over R. Its roots turn out to be complex numbers that are not real. So the original polynomial is reducible over R, but when you partially factor it over R, you are left with quadratic that's irreducible over R. It's got complex roots. If you want to confirm that, you could use the quadratic formula. You'll see you'll get a negative number under the square root, b squared minus 4ac will be negative. I mean, b squared is going to be 2 to the 2/3 minus 4 times that's going to be negative 3 to the 2/3. Square root of negative numbers is going to involve I. But it is irreducible over the rationals, this polynomial. Eisenstein, apply Eisenstein with p equal to 2. 2 does not divide the leading coefficient 1. It does divide all the other coefficients, some of which are zeros. 2 divides 0, 2 divides 0, and 2 divides negative 2. 2 squared, 4, does not divide the last constant term, negative 2. Eisenstein would be enough to verify it's irreducible. You also know it doesn't have any rational roots. And it's got degree 3, so that would be another way to say it's irreducible over Q. Anyway, coming back to this theorem now. So we're applying this theorem with p of x equal x cubed minus 2, which is irreducible over Q. A is cube root of 2. Degree of p of x is 3. So this would imply every element of this field extension can be written as a linear combination like this, with a equal to 2 to the 1/3, and n is 3, so the highest power of a will be 2. Book uses c's as the coefficients. I'm going to go simpler. Use a, b, and c. This also could be written, instead of root notation, you could also write it with power notation. Like that. Either way is fine. And I am referring, when I use these symbols, to real cube roots. There are also complex cube roots of 2 that I'm not mentioning right now. That'll be a topic for Monday. Hopefully. Wednesday for sure. These are all real numbers that are, I mean, yes, real numbers are complex numbers, but they are also real numbers here that we're talking about. So that evidently is enough to apply that this is a 3-dimensional vector space over the rationals. A basis would consist of 1 cube root of 2 and cube root of 2 squared. I mean, that would take proof to show, well, the theorem is implying this is a spanning set. You would also need to show this is a linearly independent set of numbers over the rationals. That would take proof. Actually, in the book's theorem, it does say it's unique expression. And actually, that uniqueness is enough to imply linear independence. So in proving uniqueness, that means the powers of A are all linearly independent over the base field F. So it's a 3-dimensional vector space over Q. How are these vectors? Is this vector space stuff relevant now? That's our last 10, 12 minutes or so here. Spend a little time with that. With this definition here. The degree of an extension. Let E be an extension field of F. F is the base field. E is an extension, bigger. We say E has degree n over F, and we write this. That's kind of similar to some notation from group theory, isn't it? Index of a group, of a subgroup in a bigger group. Kind of similar here. Similar notation. E is the bigger field, F is the smaller. This is n. If E has dimension n as a vector space over F, and right there, that's enough to say, why did this edition of the book get rid of the old chapter 19? It must have been a mistake. Vector space over a subfield. Yeah. Doesn't make much sense to have this in here if you're not going to have a chapter about vector spaces over fields. If this degree is finite, E is called a finite extension of F. Careful, that doesn't mean E contains finitely many numbers more than F. It contains infinitely many more. It's that this dimension is finite. Otherwise, we say it's an infinite extension. And you draw simple kind of pictures like this, including our two examples that we've looked at so far, Q of square root of 2 and Q root of 2. This example, if you can't quite see it, if it's not big enough, says Q of 6th root of 2. That's a 6-dimensional vector space over Q. Elements of that are linear combinations of powers of 2 to the 1/6 power. 0th power, which would be 1, 2 to the 1/6, 2 to the 2/6, which is the same as 2 to the 1/3, 2 to the 3/6, which is the same as 2 to the 1/2, 2 to the 4/6, same as 2 to the 2/3, 2 to the 5/6. In general, if E has degree n over F, you write that kind of picture with that's an n there. And these pictures, simple as they are, help you understand more complicated pictures that can help you understand, examples like example 4. Yeah. Well, I don't really want to understand that without pictures. Okay. The author put some pictures in there. Look at all of that. I skipped a theorem, an important theorem. Actually, a couple important theorems. Finite implies algebraic. If E is a finite extension of F, meaning the dimension of E as a vector space over F is finite, then it's an algebraic extension of F. Every element in E is algebraic over F, the root of some polynomial with coefficients in F. The proof's actually not that hard. It's fairly short. If this is dimension n, then that's a linearly dependent set over F. What does it mean for a set of vectors to be linearly dependent? It means there's some non-trivial linear combination of them that equals 0. There are C's in F, not all 0, such that that's true. That's your polynomial that A is a root of, the arbitrary A in E. Since A is arbitrary in E, every element of E must be algebraic over F. That's a pretty short proof. You should be able to do that in an exam. Pretty understandable, too, once you understand the basics. So, finite extension means algebraic. Remember that any if-then statement is also equivalent to its contrapositive. The contrapositive of this would be if E is transcendental over F, then it can't be finite. Q of pi, Q adjoint pi can't be a finite extension. As a vector space over Q, it's not going to have a finite basis. Kind of makes sense when you think about the fact that every element in it is a rational function when you plug in pi. But the converse of this is not equivalent to it, and in fact is false. If E is algebraic over F, it's not necessarily finite. Here's a quick example. Q adjoin square root of 2, cube root of 2, 4th root of 2, 5th root of 2, 6th root of 2, 7th root of 2, 8th root of 2, forever and ever and ever, is algebraic over Q because every element of it is the root of some polynomial with rational coefficients. But it's not a finite extension. The degree of this is a dimension. The dimension of this is a vector space of the rational is not finite. There's no finite basis. It kind of makes sense because you're joining infinitely many distinct elements. And this theorem is kind of analogous to Lagrange's theorem for group theory. If K is a finite extension field of E and E is a finite extension field of F, so you've got F as the bottom one, then E, and then K above E and F. And K is a common letter to use for fields, by the way, if you read a lot of algebra books. In fact, they use lowercase k's for some reason all the time for fields. Anyway, the degree of K over F, the highest field over the lowest field, is the product of the degree of K over E with E over F. Certainly not the exact same thing as Lagrange's theorem, but it's a theorem related to multiplying things or dividing things. I mean, you could rewrite this as a division as well. So it's a counting theorem, and that makes it powerful. Its proof is harder. That wouldn't be on the exam. Though it's not super hard. And the key thing is to create a basis for K over F. You end up multiplying all the basis elements for K over E with the basis elements for E over F. You consider all possible products. And there's M times N of those. You just got to prove that this is a basis. That's a useful observation for helping you understand examples as well. And let's end by peeking at example 4, though I don't think we'll have time to completely understand it by any means. Consider Q adjoin cube root of 2 and 4th root of 3. So first thing, okay, this is the smallest subfield of the real numbers. I can use the reals because these are real numbers. Containing all the rationals, also containing cube root of 2, also containing 4th root of 3. But again, it's going to contain many other numbers, infinitely many others. The claim is the degree of this extension is 12. A basis for this field as a vector space over the rationals would have 12 elements. That's the claim. I want to explain that. Clearly, this is true. Why is that true? Well, it's essentially this fact here. To understand all this stuff, look at a picture. I guess that picture there. We got this extension field we're thinking about here that we want to show is degree 12. 12-dimensional vector space over Q. There is an intermediate field here, Q adjoin cube root of 2. It is intermediate. It is a subfield of this because both of these fields do contain cube root of 2. And that's the smallest subfield of the reals containing cube root of 2 and all the rationals. So it's got to be smaller than that. And in fact, you can sort of get from here to here by just adjoining 4th root of 3. Claim is that has degree 4, which makes some sense because that's a 4th root. And this has degree 3, which we've seen already. And therefore, the degree of this entire extension has got to be 3 times 4, is what the textbook is arguing. With pure symbols here, though, it's easier to understand the picture. Though the author does argue in terms of inequalities as well. Is that really necessary? I think, yeah, the reason the author is arguing that way is maybe because the author hasn't quite proved yet that this has degree 3 and that this is a 4. We know this product is equal to that, but perhaps without looking at details, the author hasn't said what these numbers are yet. Does the author eventually say that? Okay. So the author's in saying this is equal to 3, for example, is not using the other theorem like I did a few minutes ago. The author is just saying, oh, no, excuse me. The author is using that. That's 3, that's 4. Therefore, because of this equation, 3 divides that. Because this thing's a 3. 3 times something equals something. 3's got to divide that. And from a similar equation, not the exact same equation, by extending the diagram over this way, knowing this number is 4 and knowing that's right there, means 4 also divides what we're interested in showing as 12. So 3 and 4 both divide this number. Yeah, it's enough to say this number is a multiple of 12, but not necessarily equal to 12. It's greater than or equal to 12. On the other hand, the author says this thing is at most 4, since the 4th root of 3 is a 0 of x to the 4th minus 3. In here, we're thinking of it as an element of that, which we certainly can do. The author doesn't say that this is irreducible over that field. And that's why he uses at most 4 instead of exactly 4. Maybe there's a lower degree polynomial in which this is a 0 of over that field. Certainly that's the smallest degree polynomial with coefficients in Q in which this is a 0, but with coefficients in Q adjoining Q root of 2, maybe there's something smaller degree. So it's at most 4. That's why he doesn't say equals 4. Anyway, those arguments can come together to say this is 12. So, I mean, the hardest part about this is all the crazy symbols, I think. The idea is fairly simple if you think of it in terms of a picture. Relatively simple, not fairly simple. Relative to looking at all this. Here is an example similar to what I was talking about on Wednesday. Yeah. So you should take the time to study this in more depth. The next chapter is also about finite fields in more depth, which is very important as well. But I think next Monday, we're certainly going to start talking a little bit about Galois theory, because that's the very end topic and maybe the hardest topic of them all. So we want to start talking about it. What you get tested on for Galois theory is relatively simple in the big scheme of things of Galois theory, but to even understand the basics is going to take some work.